All right, we'll continue. So what we did in the previous segment was use this mapping between the parent and physical element subdomains to observe that we have actually a convenient way of writing out our gradients. Okay, we'll continue now from there and consider explicitly the three integrals that go into our weak form. Okay, so with that background, now we are getting into actually assembling the integrals in the finite dimensional weak form. Okay, the integrals in the finite dimensional weak form. Okay, so let's consider the first of our integrals, right? So we are going to consider this one, integral over omega e wh comma I jh I dv. Okay, we'll first invoke our constitutive relation to write this as integral over omega e wh comma I. We pick up a minus sign here, minus kappa ij uh comma j dv. Okay, that minus sign just came from the fact that the flux is written as minus the conductivity tensor multiplying the gradient of the field of interest, right, or the gradient of our trial solution field. Okay, we'll take care of that minus sign later on. Okay, so we have this, and now essentially what we are going to do is use what we've just discovered about writing out the gradients of WH and UH, right? Okay, so over element E, this lets us write it out as integral over element over omega E, right, of WH comma I we will write as sum over A. I'm not going to write the limits on A, right? We know the limits, they go from 1 to number of nodes in the element. Well, okay, let me write them as always for the very first time and then I'll abandon writing them. Okay, sum over the nodes in the element NA comma I C A E. I'll put parentheses on that. Kappa ij. Okay. Open another set of parentheses for a sum over B going from 1 to number of nodes in the element. Okay. NB comma J D A E dV, and we have a minus sign. Okay, and as we did in the 1D case, it's perhaps useful to just remind ourselves that that is WH comma I and that is UH comma J. Okay, and now we use our discovery of how to write those gradients of basis functions, noting that those gradients as expressed here are gradients with respect to physical coordinates, right? Okay, so this is now integral over omega E minus integral over omega E, open the first set of parentheses, sum over A, and I'm going to abandon writing the limits from here on. Now, NA comma capital I Okay, and recall that when I write NA comma capital I, we're talking of taking derivatives with respect to what? Right, with respect to the coordinates in the parent subdomain, right? This times Ci comma little I, okay, multiplying C A E, okay, kappa ij, open parentheses again, sum over B, abandoning limits, NB, comma, capital J, C J, comma, little j, D, B, E, dV. And I note now that I was not quite as careful when I wrote that. That's not a DAE, that is a DBE. Okay? Right. Note that what I'm doing here is just partial of Ci with respect to x little I. Okay? Same thing here. Okay? Partial of C capital J with respect to x little j. Okay? And this is partial of n a, the a basis function, the basis function for node A, or the basis function which is 1 at node A, with respect to C capital I. And this is okay. Right? Fine. So we know how to compute these quantities now, right? Okay. So let's move on, and actually let's make our expression here a little simpler by observing that the degrees of freedom, of course, are independent of position, and therefore they can be pulled out of the integral. Okay? So we'll take the step that we have taken before in the 1D problem. This is equal to minus. Now, sum over A and B. Okay, we have here C A E integral over omega E N A comma I C capital I comma little I kappa ij n b comma capital J C capital J little j. Okay, all of this integral dv. And just for complete clarity, I'm going to put parentheses on this, right, on the integral, and note that the whole thing is then multiplied by dBE. Okay, some things to note. Though perhaps one way to think about this is that we have an integral, right, and we have a complicated looking integrand here. Okay, each integrand, right, has indices A and B, right, and these indices A and B come from the particular degrees of freedom over the element that we're talking about, right. So this would be, so the picture here would be, let me draw it here. So the picture here would be in the physical domain, we have our element and we have a node A, right. or B. Okay, the index A or B runs over those nodes, right? It runs over the degrees of freedom that correspond to the nodes, right? And over the others, of course, right? It runs over all of those. Okay, so having chosen a particular combination of degrees of freedom for A and B, right? Okay, for that particular combination of A and B, we have the functions NA and NB. Okay, now inside of our integrand, observe that there is another set of multiplications happening, and I'm trying to look for a different color here. There we go. Okay, using green. Okay, inside the integrand there is Einstein's summation convention implied all over the place. Okay, so there's Einstein's summation convention here. Okay, here, here, as well as here. Okay, again, if you've studied continuum physics and done this in 3 dimensions, you've probably seen this sort of thing often. Okay, so whereas we have Einstein's summation convention for summing over indices that correspond to either physical or parent domain coordinates, that's what the little ij and the capital IJ refer to, right? We have used an explicit sum there to run over the degrees of freedom of the element. Okay, I just want to make this a little bit clear. Okay, so if that part is clear, we'll proceed, and in order to proceed, we observe that the way I've written it out so far, even though we've actually moved over to writing our computing derivatives with respect to the parent subdomain coordinates, our integral is still over the physical element, right? And that elemental volume here really refers to the physical element. Okay, the next step we're going to take is to convert this also into an integral over the parent subdomain. Okay, so now we are properly changing variables into the parent subdomain. Okay, so we are really completing change of variables to C. All right, and what that means is that we need to essentially convert the elemental volume. Okay, now here is our map. Okay, okay, that's omega E, and this is constructed, of course, from omega C. Okay, and we have our map x of C, right? So for an arbitrary point, physical point little x here, and an arbitrary point C in the parent subdomain. Okay, what you want to think now about is how do we represent the elemental volumes, right? And in order to do that, consider the fact that we have here an elemental volume. Okay, that's my D capital V. And here we have an elemental volume that I'm going to represent as D V C. Okay, dV sup Xi, just telling us that that's an elemental volume in the parent subdomain. Now, another result from the fact that we have this mapping and that we also have the tangent map J of Xi. A result that follows from this is the following. One can show that dV equals determinant of J dV Xi. Okay? This is a standard result. If you've ever played around with these sorts of configurations, it can be proven, and it's conventionally done if you're studying kinematics of deformable bodies. Okay? But we are just going to use this result. Okay? We're essentially going to use this result in our integral, right, that we're working with, this one, right? And we're going to try to replace that elemental volume with this expression, right? That is, however, perhaps best done in a separate segment. So we'll stop this segment here.